How can the model get to the best point? Maybe it was trained using gradient descent, which is an optimization technique. Let us discuss what a gradient is and why we need to descend. The gradient of a function f is an n-dimensional vector of partial derivatives. For example, if a function depends on 3 variables, a function, then its gradient will be equal to like that. In this case, the gradient defines the direction of the fastest growth of the function. So, the antigradient will show the direction of its fastest decrease, which will be useful in our problem of minimizing the error functional. Generally, gradient descent is a method of finding a local minimum by moving along the gradient. Let's try to implement gradient descent programmatically to better understand how it works. Firstly, define two functions, the parabola function and the derivative of the parabola function. We can draw this function on the graph. Indeed, we see a parabola. To find the minimum of this function, we can use the optimization method, gradient descent. For this, we need to set a starting point, from where we will count gradients and roll down to the minimum. In the graph, the green start is the starting point. Now we can calculate the gradient at this point. It is equal to 10 because the starting point is 5, and the derivative will be equal to 2 times 5. Now we can draw the direction of the gradient. It shows the fastest growth of the function, and indeed we can see the green vector goes up. But if we move along this vector, we will not come to the minimum of the function. So we need to move the opposite direction, and therefore take the anti-gradient. But if we move from the current point 5 towards the anti-gradient du, we will end up at point -5, which is as far from the minimum as our starting point. Therefore, in order not to jump the minimum state of the function, we can make a step towards anti-gradient not completely, but only by some fraction. For this purpose, we need to introduce values of the learning rate. Learning rate are values that slow down the steps of the gradient descent in order not to miss the local minimum. Now we have a new point with coordinate x equals 4, and we can calculate the gradient value in this point again. Draw the direction of the gradient, which shows the fastest growth of the function, and mark in blue the already passed step. But if we move along this vector, we will not come to the minimum of the function. So we need to go in the opposite direction and therefore take the anti-gradient. At the same time, we remember that if we go to the full anti-gradient, we can overfly the minimum. So we multiply by the learning rate, and we obtain another point, which is already closer to the minimum of the function. Let us form a small cycle for gradient descent and go through 10 steps and find that we are almost at the minimum of the function. And if we do more iterations, the algorithm will probably converge to 0. But here the values of the best minimum point at the last steps are very similar. And in fact, we could not wait for so many iterations and leave the loop earlier. For this purpose, we introduce the value epsilon with which we will check the difference between the current point and the next point, and if it is less than epsilon, which means that the points are very close, we can exit the algorithm. And yes, the algorithm needed only 42 iterations. The difference between the 2 points was less than epsilon, so we can exit the convergence loop of the algorithm. This is called a stopping criterion. Now knowing how the gradient descent optimization method works, we can return to the task of linear regression training, but not with the help of special library, but manually. We take the same data, but in addition we return the slope coefficient. The default shift coefficient in this generation is 0. The function we optimize here is mean squared error, and its graph for our particular problem was drawn here. Mean squared error and the gradient of the error function. Let's write it separately for the shear and slope coefficient. And it remains to start the gradient descent loop. At the beginning, we initialize the coefficients. Then at each step, we read the gradient. Multiply it by the training step and subtract it from the previous coefficient values, and so on until we understand that the coefficient points are very similar to each other at the neighboring iterations. Let's compare the obtained coefficients with those generated with the data. Exactly, we obtained exactly the same metric that was obtained by linear regression, and they're very similar. These visualized curves are layered on top of each other. All right, now we take the same data where we took 4 features, but we also return weights for the features. And the default free weight in this generation is 0. For convenience in implementing the gradient descent, it is need to switch to the matrix form of notation. Predictions of the linear model are multiplication of weights by features plus free weight. It is very important that the dimensions of the matrix X and the vector W to be equal. Yes, we have equal dimensions. It means that the number of columns of the first matrix should be equal to the number of rows of the second matrix, but we do not have a matrix, but a vector. They coincide so we can multiply them and get nothing but a scalar product. All values in the attributes are multiplied by the corresponding weights and added together. So we can rewrite the formula, but the only thing that gets in the way is the free weight. We can go for one trick and add a dummy feature to the data, which is equal to 1 for each object. And now the entire prediction of the linear model will be equal, and our mean squared error will be transformed and will look as follows. And our mean squared error will be transformed and will look like this, where L2 norm is used like that. Let's realize 2 functions only already with matrix operations. Mean square error function for matrices and gradient of error function for matrix, and it remains to run the gradient descent loop. At the beginning, we initialize the coefficients. Since we have 5 features, 4 real ones plus 1 dummy one, we will have 5 weights. Then we run the learning loop and change the weights, not each weight separately, but all the weights together at once. And if the weights start to change badly, we can exit by the stopping criterion. We left the training cycle early because the weights stopped changing much and we started treading on the same place. Now let's compare the obtained coefficients with those that were generated with the data. Thank you for watching and enjoying the video. You can find the code used in this video in the description below. Stay tuned for more content and see you again soon.